Alright, this is the second lecture for Text Unit 2 on matter. Previous lecture dealt with elements. This lecture deals with compounds, in particular, their formulas and names. A compound is a substance which contains two or more elements, always present in the same relative amount. For example, water, famous compound, is always 11% hydrogen and 89% oxygen by mass. And later in this course, we'll actually learn how to determine these percentages. But these percentages are true for every sample of the compound water. Compounds fall into two categories. The first we'll examine is molecular compounds. Molecular compounds are made of two or more nonmetals. Remember, the nonmetals are on the right-hand side of the periodic table. And the atoms in a molecular compound are held together in molecules by bonds. And at this point, you should simply think of as a molecule as a cluster of atoms, and a bond is something that sticks two atoms together. When you name a compound made of two nonmetals, take the leftmost element on the periodic table first, then take the rightmost element on the periodic table and end it in IDE. Prefixes are used to tell how many atoms of each element there are per molecule. The prefixes are listed in Table 2.1 of the text, and you'll see mono meaning one. This one actually receives very little usage. Di meaning 2, tri meaning 3, tetra meaning 4, penta for 5, hexa, hepta, octa, nona, deca for 6, 7, 8, 9, 10, respectively. At this point, we should mention that there are molecules made of elements before we go on to say more about compounds made of molecules. Elements made of molecules that you will need to know for this course are the diatomic elements, hydrogen, nitrogen, and oxygen, and the halogens, fluorine, chlorine, iodine, and bromine. And when we discuss these elements as they occur in nature, they will always appear as diatomic molecules. For molecular compounds, the formula is written with symbols for elements in the same order as naming, in other words, left to right on the periodic table, with subscripts to tell how many atoms of each element there are per molecule. So, for example, water has the formula H2O, and if you're provided with that formula, you know that the name of it has to be dihydrogen oxide. Hydrogen is on to the left of the periodic table, oxygen is further to the right. You should be able to go write down a name if given a formula, or a formula if given a name. Here are some opportunities to practice. Formulas are here. Unfortunately, the numbers are not subscripted. Systematic names are over here. So, for example, NF3 is nitrogen trifluoride. NO is nitrogen monoxide. NO2 is nitrogen dioxide. N2O is dinitrogen oxide, etc. Notice that there is one example of the use of the mon prefix in nitrogen monoxide. More on that in a moment. SF10 would be disulfur decafluoride. H2O, as we mentioned, is dihydrogen oxide. H2S is dihydrogen sulfide. We have nitrogen trihydride, dinitrogen tetrahydride, and phosphorus trihydride. And there are no examples with the mon prefix on this in this set. It's logical at this point to wonder when to use the mon prefix. For this course, there are two compounds where the mon prefix will be used. Carbon monoxide, CO, and this is done principally to distinguish it from carbon dioxide, and nitrogen monoxide, NO, and again the prefix is used principally to distinguish it from nitrogen dioxide. Ionic compounds, as opposed to molecular compounds, are made of ions. Ions are charged atoms, as we have seen. A positive ion is called a cation, and a negative ion is called an anion. Ionic compounds are held together because positive charges stick to negative charges and vice versa. This implies that every ionic compound will have positive and negative charges, and in an ionic compound, a typical ionic compound, there will be a metal, and the atoms of metal supply the cations, and a nonmetal, and the nonmetal atoms will be the anions. Charges of ions may be determined from the periodic table. This is summarized in Table 2.2, which is you will be responsible for knowing. Alkali metals, the first column on the left, all form ions with a +1 charge. Alkaline earth metals, second column on the left, all form charges of +2 when they are in ionic compounds. Halogen atoms have charges of -1 when they are in ionic compounds. Other nonmetals may be found, and notice that the halogens are nonmetals. Other nonmetals may be found in the column immediately to the left. These form ions with a -2 charge in ionic compounds. This column includes sulfur, oxygen, etc. The column to the left of that forms ions with a -3 charge in ionic compounds. This includes nitrogen and phosphorus, etc. In the formula for any ionic compound, charges must balance, which is to say there are the same number of positive and negative charges. When naming ionic compounds, first place the cation first, and then the anion. If the anion is made from an element, as we've seen so far, it ends in IDE. So, for example, sodium chloride is an ionic compound. You could tell it's ionic because it includes the metal sodium. It has a formula NaCl, 1 positive charge to 1 negative charge. Magnesium chloride is an ionic compound because it contains the metal magnesium and the nonmetal chlorine. Attempt to write its formula down before looking at its example further on in the presentation. The formula for magnesium chloride is MgCl2. Magnesium has a +2 charge, so 2 chloride ions are used to balance the charge. So there are 2 chlorides for every magnesium. Note that this formula does not show the charge of the magnesium cation or the chloride ion. Formulas for compounds do not show charges. Subscripts show that there are 2 chlorines for every magnesium to balance the charge. Subscripts should always be the smallest possible set of whole numbers that balances charge. And you don't have to put a 1 because there's only 1 magnesium. Keeping that in mind, write down formulas for sodium oxide, barium oxide, calcium phosphide, and aluminum chloride. And before you attempt aluminum chloride, you should know that the aluminum atom forms a cation with a +3 charge in ionic compounds. That is also stated in the text. Stop the presentation, attempt formulas, and then move on to see the solutions. when you look at solutions, sodium oxide is Na2O. Oxide has a -2 charge, so it takes 2 sodium charges to balance the charge. Barium oxide, barium has a +2, oxygen has a -2, so a 1-to-1 ratio of atoms balances the charge, and this is the formula for barium oxide. Calcium cations have a +2 charge. Phosphide anions have a -3 charge from the table. So 3 calciums produces a +6 charge, which is balanced by a -6 charge from 2 phosphides, and Ca3P2 is the correct formula for calcium phosphide. Aluminum chloride, again, the aluminum cation has a +3 charge, so the formula must be AlCl3. 3 -1 chloride ions balance the +3 charge of the aluminum. Unfortunately, there are complications to naming ionic compounds. The first complication we will consider is the existence of polyatomic ions. A polyatomic ion can be considered a molecule with a charge, or ions made of more than one atom. These behave just like monatomic or elemental ions in naming or formulas. Put the name or formula of the polyatomic ion in the appropriate place. Polyatomic ions appear in Table 2.3 of the text, and you'll be responsible for knowing the contents of this table. One cationic polyatomic ion is ammonium. Written by itself, you see the formula here, which shows the +1 charge of ammonium. That charge will not be included in formulas for compounds. Most of the polyatomic ions are anions. Hydroxide is an OH with a negative charge, for example. Carbonate is a 3O3 with a -2 charge. Chromate has a chromium 4 oxygens and a -2 charge, and so on. Again, given a name, you should be able to produce a formula, or a formula, you should be able to produce a name. So try writing the formula of barium hydroxide, ammonium phosphate, and potassium sulfate. Barium is a cation with a +2 charge, and so there will need to be 2 hydroxides, each with a -1 charge, to balance the charge. So the formula must be BaOH2. Note the use of parentheses to indicate that the 2 applies to both atoms of the hydroxide. So OH parentheses 2 means 2 hydroxides. Ammonium phosphate requires 3 +1 ammonium cations to balance the charge of the phosphate anion. So the formula of the compound is NH43PO4 is written. Potassium sulfate requires 2 potassium cations to balance the charge of the sulfate anion, and its formula appears as shown. Alright, this concludes the second lecture in Unit 2.